The problem states that if we suspend a metal ball from a rubber band and twist it many times around its vertical axis and release the ball, then standing waves may form on the band. Our goal is to investigate this phenomenon and study how the wave depends on relevant parameters. So what happens first is that we first attach the band to the ball, and we assume that the band is homogeneous and viscoelastic, and that the stress of the attachment is negligible. After that, we suspend the ball from the fixed point, and thus the band is stretched, and assuming that the band mass is negligible compared to the ball mass, we assume constant tension and uniform stress. After that, we twist the band while we hold the ball, and thus torsional energy is stored in the band, and also the band stretches further on. After that, we release the ball, and we assume that the system behaves as a torsional pendulum, and as it starts to untwist, given the initial imperfections in the band and the precession of the ball, transverse waves may appear, and given the fixed point and the ball with the large amount of inertia, standing waves form one after another. And as the system changes standing modes, the system enters transient states, and to better understand this phenomenon, let's look at it also from an energetical approach. So the initial state is that the torsional energy is at its maximum, and after we release the ball, the restoring torque accelerates the system, and the torsional energy is converted into kinetic rotation energy. And after that, when the energy is at its maximum, the system reaches the maximum velocity, and we assume that the maximum number of modes form when this kinetic energy is at its maximum. After that, the band twists back, and this goes further on, and the loss is y increases to this velocity. So let's look at the relevant parameters of this phenomenon. For the band, the number of twists, the mass, the radius, and the length of the band, and the relevant elastic parameters are the Young's modulus, E, and from this we can calculate the shear modulus P, which relates the stress and the strain during different deformations. For the ball, the most important parameter is the moment of inertia of the ball, which includes the radius and the mass of the ball. We measure the Young's modulus by applying masses to the band, and we watched how the length of it changed, and from this we can calculate the Young's modulus, and from that the shear modulus with the given Parsons ratio. Now onto our experimental setup. The experimental setup consists of a stepper motor with a clutch, and we use silicone rubber band and a metal ball. We use a stepper motor to calibrate the number of twists, and we use the clutch to ensure symmetric fixed end for the attachment. To attach the ball and the band, we use a screw where we put a hole, and in the hole we inserted the band and glued it with silicone glue. Thus the symmetry of the system remained. And we use silicone band as it is more homogeneous and is easily variable for the parameters. For the balls, we use the different masses and diameters, and here you can see the different balls that we used. To extract data, we mark points on the band and the ball and took videos from fixed position and evaluated in track. Now onto the theoretical model. As I mentioned before, we modeled the system as a torsional pendulum, where the torsional stiffness relates the torsional angle and the torque acting on the given point of the band. And following the analogy of the natural frequency of a spring system, we can define the natural frequency of this torsional vibration. After that, we modeled the rubber band as a stretched string that supports transverse waves, and considering the boundary conditions, which is the fixed end and the ball with the large amount of inertia standing ways from, and we can define the natural frequency of the wave for a given mode with the following equation. As I mentioned before, the system reaches maximum velocity when the torsion energy fully turns into the rotational energy. And from this relation, we get the maximum angular velocity. And given the conditions that the modes that form cannot exceed this angular velocity, then we can define the maximum modes that form on the band for the given equation. And we need to include losses, which we included for the maximum angular velocity in the given form. So what are the different losses which done the system? We defined the viscoelastic internal drag of the band and the air drag acting on the band and the ball. So the effective loss of the system tells us how much energy goes into damping per one period of this torsional oscillation. So we can write the following for the effective loss and define the average power, and this equation tells us the effective loss of each part of this equation. Now let's model the viscoelastic loss. We use the Kelvin-Ward model, which models material elastic on long time scales and shows extra resistance to fast deformation. And this includes the damping, and from this we can define the average power and get the effective viscoelastic damping. After that, we model the drag force acting on the band, and we could calculate the average power from it, and thus we get the following equation for the effective damping on the band given the air drag. Now, we can see that the drag includes the maximum velocity, which is problematic because we need to define it from the damping. And this creates a cyclic definition, which so we call the half of the number W function in Python. And this we could solve the problem here. So to model the air drag acting on the ball, we used the Stokes law, which assumes that the laminar flow around the ball rotating in is in a fluid. So we could also calculate the average power, and we assume that this fluid is the air here, and we can see that the measurements in the theory match quite well for the drag, so this is an effective method to calculate it. Now we can see the final equation for the maximum number of modes that can form, and we can see the approximate proportionalities. We investigated the rotation of the ball also, and we can see that the rotation of the ball is sinusoidal, so we can indeed define it as a torsional pendulum. And yes, so now onto our results and comparison. We created a simulation for the following equation, which determined the maximum mode numbers that can form. And as you can see, that only integer modes are present. So we use the floor function in Python, and we did 3 measurements for each configurations, and from this comes the error. Now we can see more examples for more parameters, and we can see that the theory matches quite well. But on the left side, we can see that the theory over-exceeds the measurements, and it comes from that after a critical number of twists, the band tangles and the number of modes decrease significantly. And it is because initially, when the twist reaches a maximum, the straight configuration becomes unstable, and thus buckling happens. And we can see this coiling, and this is why the standing waves still appear, but they are reduced. We compared different bands, and we can see that as we increase the radius, the maximum number of modes that form still increase. And we can see this for each configuration, and the goal here was to compare different parameters to compare proportionalities. And we can see the damping is lower on thinner bands, so the waves can form for a longer time, and it can also withstand the higher number of twists. So we have also compared different balls, and we can see that when we increase the mass, the inertia also increased, and we can see reduced obstacle modes. And when the ball was too light, we could see increased number of modes, but the band angled after a few twists. And we have also compared different band lengths, and we can see that that in the theory, the length wasn't included in the mean equation, only in the damping, and we can see that there's a slight dependence because of that. So we can see that the drag is distributed more in longer band, and therefore there's less damping, and we have also compared this part with the theory, and we can see that the theory also predicts this pretty well. So in summary, we investigated all the relevant parameters of this problem, including the band and the ball and the number of twists. We measured the Young's modulus, and thus we could calculate the shear modulus and use it in our simulation and a numerical solution. And also we defined this as a torsional pendulum working. So we wrote an equation for each frequencies that happen, and also we wrote down the damping mechanisms for both the viscoelastic loss and the drag acting on both the band and the ball. And we wrote a simulation to compare this theory with the given parameters, and we could also compare it very well. And we also discussed the limitations of this buckling and tangling. And then we compared the different parameters, the ball, and the bands, and we could also discuss these limitations. Thank you for your attention.
I'm very uncomfortable with the fact that both of these teams are taking photos of every single slide. What purpose is that?
So we could go back and see what was on the previous slide.
They're doing a presentation. You request to see it again. You don't take pictures of everything. I don't think you have the right to take
We
pictures of everything.
confirm it with the commission so that it's aligned with the rules.
Why not? I've never seen anyone do what you just two teams have just done.
Yes.
You have?
No.
No.
We also yesterday, like,
Well,
all time.
as I say, I've been here a long time.
Just mentioned that taking photos and videos is allowed when we are not live streaming, so it should go.
Yes,
No, that's about recording it for later looking at. That's not for being part of a competition.
But I think it was also done in the previous years.
I really.
But for me it was a bit disturbing, but I think it's...
And if it's disturbing to the person who's
Yeah,
being photographed all the time, I think it's
I think
not
they
something
can, but
that's
it's...
appropriate. I would appreciate it if you stopped doing it.
So
And then you can make a complaint if you want, but I think it's inappropriate.
okay, so we should just not use them from now on?
Well, I'm not sure how you use them to any benefit, because you have a time limit, you are responding to what's being presented. You weren't even looking at it, you just got click.
I mean, it's for the purpose that if I don't catch some slide when there were a lot of equations on one slide, then maybe we want to look back on the slides during the time of preparation to see what was.
Well,
what was on.
this is where you make notes and things, you know. I do not understand it. I mean, am I wrong here?
In general, I completely agree, but it has to be in accordance with the rules, and they don't know the rules, they don't know what to display.
I think that was distracting to the reporter.
Yeah,
I think that makes it not appropriate.
Okay, so sorry for that.
Can we move on to questions of what was actually presented? Yeah.
My name is Anna, and I would like to ask a question. So, my first question, do you explored also parameters of waves such as frequency and interactivity to the design?
Well, I couldn't extract all the amplitudes, so I didn't investigate it further.
Okay, so you only explored the number of outputs.
Yes.
Okay. Then I would like to ask why on some of your graphs, on the very end, where you change the parameters of the rope, for example, like slide number 38, for example, there is no theory overlay.
I have included that the proportionalities are there, so this is from the equation of the proportionality and something like that.
So there is no theory line going through them. Could you elaborate on that?
What theory is there?
Okay, so that was just one graph where there was a dimension. Okay. And are you sure that in this specific graphs, the parameters were changed independently?
Well, for the band, we couldn't always change it independently.
Thank you. Then I would like to ask whether you still believe that Hookean elasticity is still applicable even for a large number of twists.
For a large number of twists, it is not applicable.
And where is this borderline when you stop being applicable?
Well, I stopped after 100 twists because then it became so elastic.
Okay, thank you. Then I would like to ask on slide 21, have I understood correctly that in your theoretical model that there is assumption that the bottom end is fixed?
Yeah.
And isn't this arguing with your theoretical
Well, it is
explanation
one model
it's
that
a-
the wall should have a large amount of inertia. So,
Okay, but okay, then I would like to ask whether have you observed the change in length of the spine, and is this accounted for in your theoretical model?
well, not because the change was very small. So, like 5 millimeters or.
Okay, thank you. I think this is valid. And was anything fitted in the losses?
That we took the amplitude as
Oh,
constant.
okay, that is time. We'll have to stop there. So thank you to the reporter and do sit down. The opponent has 3 minutes to prepare. You ready?
Hello, my name is Anna, and this will be the opposition for problem number 5 from Slovakia. So the problem stated that the V should suspend a metal ball from a fixed support using a rubber band and twist it many times around its vertical axis, which I think was very nicely done because the experimental apparatus was, I think, wonderful, and I really enjoyed the way that they used the stepper motor. And then, when the ball is released, the standing waves are formed on the rubber band. And we should investigate this phenomenon and study how the wave depends on the relevant parameters. And I think this was done to an extent. I think it was really nice that we saw the variance in the rubber band used, and also the mass of the ball changed. However, I would appreciate if there were more parameters of the waves explored, such as change in amplitude, change in frequency, and actual switching of modes dependent on time. For the recorder, I would say that I really enjoyed apparatus using the stepper motor, which they could control the number of turns and the clutch they used. And I also like that they attached the ball using elastic glue, so that it's symmetrical. And I enjoyed their qualitative explanation about how the waves are formed, although I was missing explanation of switching of the modes and why are they actually switching. And I think this has to do something with resonance, since the torsional oscillation of the ball is actually lowering due to the losses that were also mentioned, and I think that these have different omegas, and therefore there is different resonance occurring and it's changing in time, and therefore the modes are switching. But I would like to check this with the reporter and what they think about this. Then I like the phenomenon demonstration. I think the video was very clear, and what I would like to praise the most was the theoretical model that accounts for losses, and it matches, I would say, fairly well with the experiments. However, I think that this still could be explored to further extent, especially the time dependencies. Although this was great, I found some questionable assumptions in the questions that were, I think, not matching with the qualitative explanation. For example, the bottom condition that the bottom end is fixed. I think this is not in accordance with their qualitative explanation, since they said that why the waves are formed is because there is some precession and change in the top of the ball and how it looks like. Maybe I would like to see a video of this to gain further insight. And I think this is kind of not the best way how to model this, since then it's questionable how, in accordance to theory, is the experiment actually started when there is not the mechanism that starts it in the theory. I would also like to say that Hughes elasticity may not always be applicable for example, large number of twists where we saw different effects happening, for example, the coiling or some irregularities in the twisting. Although I think that using silicon elastic helped with this, and it was more difficult to have these type of inconsistencies in twisting. But maybe we can talk about this further in the discussion. And then there also saw some error bars, which, for example, in some of the values of the gammas or the coefficients obtained for the losses, they did like pretty big error. I would like to talk about this further, because also the losses were kind of sped through, so I would like to gain more insight into this. And we also saw some errors in the graphs, which I think could be commented on more. And I would like to also talk about this in the discussion, and some graphs were not compared to theory, but were then further modified. So I would like to invite you for the
Okay, if we move the time on, and we have 10 minutes discussion.
I'm showing you the video.
Okay, I would like to see
You
the
mentioned you wanted to talk about this. Also,
of the ball, if I can see it from the top.
so there's this video. Well, we can see, it, of course, it's a sideways motion, and they excite each other. So
Yeah.
well, I think the phenomenon of this is mostly because of this the
Precision.
connection they have. But to make the basic theory clear, for the standing waves, we have to use this assumption that is this weight.
I understand, but I also think that this makes the theory on this part quite like not in accordance with the way what we actually observe. I think this could have been done better via more complex modeling, perhaps. Because the torsional pendulum, for example, as you stated, can you show me, for example, your equations for the torsional pendulum, where there is just the constant k term? As you also answered in the questions, like the first equation, you say that this is not applicable, for example, for large number of twists. Am I right?
Yes, because after that, if we raise for a very large number of twists, then the nonlinearity of it is pretty high. So here we can see torsional waves also forming for a very short time. So we didn't investigate it for the stable part when the molds form.
And wouldn't, for example, with this program have like longer string or?
Well, we used a longer string and we could see that the for a larger number of twists, the nonlinearity wasn't as seeable. So,
Okay, so I think that would be a nice way to kind of get over this problem, and maybe the theory would match a bit better. Then I would like to ask, during your experiment, have you observed that you twisted it and then you released it, and have you seen the number of halfways change in time?
Yes, well, for the first number of moves that were the highest formed after like 2 seconds.
And I maybe see the video, I think on the demonstration video it was really nicely visible.
And after, like, this is the shortest time, and then enters the transition state, and then it also, well, then after the band starts to untwist again, then lower number of modes form because, of course, the rotation of the ball is also slower.
And why do you think this switching of modes happens?
Well, it is mostly because of the damping. So the energy is lower after like the ball twists.
And does that mean that the precession changes as well with the losses? Or I don't see why this explanation tells us that number of halfways.
Well, I think it is intuitive that the damping influences that the larger number of modes cannot show for that long time, and after that, when it twists, the phenomenon happens again, but then it doesn't have as much number of twists, you can say. So this is my intuitive explanation.
Okay, I would say that resonance has also something to do with this, since it's inside the omega of the ball decreases. Yes, it reaches this state, and when the omega increases, there is also some angular velocity of the rope or the rubber band.
Yeah, well, we must see the angular velocity of the ball, so they are really interconnected, and this is why the phenomenon is so interesting, because they are.
Yeah, I absolutely see that. And I think that, in my opinion, I think that the switching of modes has more to do with the resonance, but I think that damping also kind of sets the pace on how fast the switching of modes.
Well, I can fully agree with you. What I meant is that also the ball twists back so smaller, so that the resonance between them is also really important.
Okay, perfect. I think we have an agreement on this. Talking about losses, I would maybe like to see some of the slides of the losses because there were many coefficients. I was not sure how were obtained. For example, the small gamma and the large gamma. I think
yes,
slide 26, for example. Yeah, here. So here we have like gamma viscous and
yes, in terms of damping coefficient. So it's literature data.
It's value from literature.
Oh, it's the so it's by definition we put together the parameters.
Okay, so these equations are from some paper.
Yes, carrying one model is one.
Okay, and how is the gamma obtained? That's some property
No,
of the system, right?
so we put together parameters because otherwise it would be really long. It's there. The equation.
This is equation for large gamma. Okay, and what's the small gamma?
Small gamma is the movement, so this is the damping term.
Oh, damping term. Okay, thank you. I understand now. And okay, so this was calculated by your data.
Yes.
And this R here, that's the radius of the.
And the band, yes.
Okay. And how do you calculate this radius? Do you take the radius when it's untwisted?
Well, it changes, but we treat it as a constant initial radius of the bands because as we investigate the stable point, then it is at the highest point, so the radius is not as significant as when it is.
But the R is to the power of 4th. I would say that it is quite a large effect when there is some imprecision in the measurement of it. So once again, can you clarify, this is
the radius of the band.
The radius of the band. Yes, it's taken when it's untwisted or when it's twisted.
When it's untwisted.
Okay. And don't you think that the radius changes a little bit when it's twisting?
Well, it of course changes a little bit. We took it as constant, otherwise.
I would say that R to the power of 4th can have quite large effect. Maybe constant is okay to be assumed, but maybe I would measure it when it's in the state of twisting and being held down. Then I would like to also ask about this new internal damping coefficient. Was this fitted or?
No, it's literature data.
It's literature data.
Yeah, for the silicon.
For silicon.
And we also used it for the latex. So we had one latex pen.
Okay. And this is from literature.
Yes, yes.
Okay. I think that's wonderful. Then I would like to ask how, like you have many different sources of damping. Which one is, in your opinion, the most important?
The most important one is the drag acting on the band. In our simulation, it came up as the highest one.
The highest one.
Yeah, but also the viscoelastic one is very important because that's one of the.
Okay, and you calculated the theory numerically.
Yes.
Okay. Then I would like to ask on some graphs where you have the number of moles, like the steppy ones.
Yeah.
We see that for some number of twists there's like zero moles, like you don't see anything.
Yes.
And have you would you say that experimentally you observed this border? Like what is the sufficient number of twists for the phenomenon to actually be observed?
Well, for different parameters, it is different of what can be seen. So yes, we investigated this as a boundary that very small twists don't make an impact. For example, for this.
Okay, and why would you say this is so?
Well, it's mostly because the rotation of the ball cannot transfer as much energy. So they are so intertwined that it also controls that how many moves we can see, and if it's a really slow, that it is intuitive.
Okay, I think I would agree with that, but I also think that since number of twists with your amazing apparatus is easily measurable value, I would maybe do the points in this interesting region when the modes are switching to have more experimental points.
Oh, so you mean for the switching of between 10 and 20?
Yeah, for example, there are more experimental
I
points.
agree, that would be really interesting for each.
Then maybe let's return to the demonstration video in the very beginning. Because you assume that the amplitude is constant. And I'm not
Should
sure.
I start?
Okay.
Well, for when the number of modes are at its maximum, so for the stable.
Okay, so you assume that it's only for the maximum. So your theory only predicts the maximum number of modes and not the time dependency.
No, it doesn't depend. Well, I have measured, but I didn't put it because the theory can predict the time.
Okay, so I think that your theory predicts really well this number of maximum twists. However, I think this problem has much more to be explored because as we see
the transit states.
Yeah, obviously. And since it says that the number of modes may switch even in the problem statement, I think this was one thing that should be observed to a little bit of a greater extent. Perhaps by somehow tracking also the position of the rubber band in the video. Some analysis of maybe do some FFT of the video would give us some frequencies, or if there is a superposition.
That's a really nice idea. It's a really complex.
Yeah, definitely it's complex, but I think it would give a further insight.
And our tracker couldn't always form this because the band wasn't always seeable.
Yeah. I understand there is also like motion blur. Okay, thank you for the discussion. I would like to
Unfortunately,
summarize
that is time. So we have 1 minute for the opponent to summarize.
Okay, so first of all, thank you for this amazing discussion. First thing that we discussed was assumption of the fixed bottom end, which we were talking about, and the theory assumption is not really with accordance to the qualitative explanation. It was only an approximation for them to be able to calculate the theory. Then we discussed the number of half waves and how it changes in time, where the reporter stated it's due to damping, and I think damping is the cause of the change in omega, and therefore resonance is what's actually like the physical phenomenon that causes this. And I think it was quite a shame that they only explored theoretically the maximum number of half waves, since the time dependency, in my opinion, would be the most interesting thing here. Then we kind of clarified the energy losses calculation and what were the coefficients that were really sped through in the presentation. And then we also discussed some of the graphs and deviations or perhaps the boundary conditions needed.
Okay, thank you very much. We can have both the reporter and the opponent standing up so the reviewer can ask some questions.
First, I would like to ask the reporter, have you considered a Neophocam model for your theoretical?
Sorry, which model?
Neophocam model. Okay, then second question, have you considered hysteresis?
Well, I didn't consider as realistic homogeneity.
Uh,
So use, yeah, I didn't consider.
Alright, Apollon, do you think that with the same angular velocity they may exist the same amount of with a different angular velocity?
I think it's possible when you have like different lengths of the spring. It all depends on the parameters of it. But for the same spring, I would say that only one number of modes or perhaps some superposition, but that's difficult to say since we didn't have like further exploration of the shape of the
So you think it all depends on the parameter of the length?
for example, the length, yes.
Okay. May I ask, how did you differentiate the zero modes from the first mode from the second mode?
Well,
Did you
we can see it from with the eye.
Okay, so only by looking at it.
Yeah, and also we checked the tracker, but it's quite visible.
Okay. Have you also considered the minimum weight of the ball that should be placed on the rubber?
Well, it's a limitation that before like 10 grams didn't really work because then it twisted easily. So it should have a large moment of inertia, yes. I can show you, but
Large enough. Okay, and and have you considered all the vertical movement of the ball?
yes. Well, it was a qualitative dimension that it also stretches, but it's a really small amount. So.
Do you think it affects the formation of the modes?
Excuse me, can I interrupt? Can we stop having screens being put up unless he's asking about them? Just pause the time for a second to get some more seconds back.
So yeah,
Okay,
did you consider the vertical oscillations, and do you think if it affects the formation of modes?
Well, the maximum number of modes form when it is at the maximum, the vertical movement. So it affects them when it happens, but the values itself, they don't change. So it's not a parameter, it's just the effect.
I think that the maximum number of halfways can be observed in the very beginning after the second mention because then damping occurs. So that's the maximum velocity that the ball is going to have.
Wait, but the vertical, like the vertical displacement, does affect the formation?
I think it may affect it because the strain perhaps changes or the stress in the stress in the rubber band may change. But she said it was because of the material she used. It was more or less like a few centimeters or millimeters. So it's not too big, I think.
Okay, thank you. Thanks very much. You now have 2 minutes to prepare your review. It's when he's ready. It's got the time. He wants to use it. No, let him finish. Okay, start time.
My name is Kyoto Provost. I'm the representative of the Hong Kong team, and I'll be reviewing the discussion for the problem of elastic wave dynamics. The statement of the problem as follows, and the task that we consider to be very important for this problem are qualitatively explaining the phenomena, modeling the dynamics of the motion of the rubber band, and conditions for the end modes to appear, and parameters analysis. Talking about report summary, the reporter actually, I really like the explanation of qualitatively part, the assumptions that they made, and the explanation of the torsional pendulum, how the transfers move and affect the standing waves, and the occurrence of the transient states, which I think really important for this task. Also, I like the theory with Collingwood model and Stokes law. They, as opponent mentioned, they considered all the losses, which is really important. And for experiment, I like the setup and how it was, how they set the number of rotations and analysis. The strength of the presenter is the repeatable experiments that derive the formula, and the experiments, we can consider them to be pretty much clear. And for the points of improvement, they could also try to use like the meaning of their model was kind of unclear for me, and I would prefer the analysis of the entire string, which we can talk about a bit later. And yeah, talking about the opposition summary, they noted the underlying assumptions. They agreed with the reporter on the use of energy model and losses. And talking about experiment, they overall agreed and praised the use of silicon rubber. And with analysis, they identified the good theory experiment agreement, which I can also agree with. The strength of the opponent is they clarified some of the parameters, and they talk about the damping on slide 26, which is very important for this task. And they pointed out the boundary condition, which is also important. But they could have added more of their own opinion, but because the whole conversation, I heard them just agreeing with each other. I couldn't have heard the actual opposition ideas. Basically, the problems that were discussed was the damping, and the opponent wanted to know if it would change to time, like the number of modes would change with time, and the reporter said it's because of damping. Our opinion is that it is because it is more likely an oscillator of the torsion pendulum, not mainly because of the damping. And they have also discussed if the radius changed when twisted. The reporter said a little bit, and it's almost constant. We actually, and opponents stated that it should change with time. We also agree with the opponent because the radius actively changes throughout the experiments due to pointing effects, and it could also be investigated. Number of how waves change with time. The opponent stated that it is mainly due to angular velocity and resonance, and the reporter said that it was due to damping. Our opinion is that we agree with the opponent. The resonance of the frequency should remain the main point, and actually I would also consider the hysteresis, because it is very important for this task, as the modes may form with the same, with the different angular velocity. The same number of modes may occur. The missed points and our suggestions is that they could have tracked with multiple cameras and then built a 3D model tracking the absolute deviation from the central line, and they could have also placed the camera on the bottom, tracking the angular velocity more precisely, and therefore calculating the damping. For the model of vertical motion against time, attention is very important, and it reduces drastically if there is vertical motion. Basically, by tracking the overall rubber band from different positions, you could have tracked the change of length, which actually is connected with the tension of the rubber band, which I think is the main part of the exploration of theory. Also, this task is about waves, but I didn't hear much discussion about the amplitude, about wavelength. I just heard that it all comes to the number of modes, which in the end wasn't clear enough. Because, like, how do you differentiate the transitional processes? Maybe you should look at the peaks at their movement, or maybe when the overall sinusoidal, like, interceptions with the
Okay,
central line.
haven't to
Right.
stop you there. That is your time. Thank you very much.
Thank you so much for this question.
We move back to the reporter for concluding remarks.
I would like to thank you for the discussion and the review. I would like to clarify that for tracking the balls, we will only use it for the damping and we track the turns of it. And we also assume the constant radius because the change during strain was very, very small. Also for the amplitude, it was a really good point that we discussed that. And we tried tracking it, but as we can see, it is a really small amount, so it's like 1 centimeter, the change of amplitude for like a maximum. It was really hard to investigate this because the errors could have been so high. Also, it was really interesting that we could discuss the time change, and we also talked about the hysteresis was mentioned. However, given the material of the band, the viscoelastic material, I don't think that this is as important as it was mentioned. Also for the damping that changes the modes, I could say that it changes the omega, the oscillation, the torsional natural frequency, and because if there wouldn't be any damping, then I think that it would respect fully and then the same amount of modes may appear. So I think it was really interesting that we also discussed this interference, because this is what the main phenomenon is. Also, yes, I would like to thank you for the discussion, review, and I would like to thank you all for.
Okay, thank you very much. If we get all three, the report of the opponent and reviewer, we will move on to questions from the jury. Yeah, just get them all focusing. Okay, if we keep going. So, question.
Yeah, this is to the reporter. This is a rubber band and you twist it. And why do you think that the tension is constant? You said the tension constant even in the field.
It's a light assumption because tension in the in the dynamic part it changes with the transient states. But we investigated the state. So when the maximum number of moles form, then the tension is
So tension is constant or not?
No. During the dynamic motions, no, it's not constant, but we assume it's a light assumption. Tension is constant.
Yeah, I'd like to ask a question to address the question to the reviewer team. Could you please elaborate on the hysteresis effect, which you stressed a lot during your review?
Yeah, because while investigating this task, I came to the conclusion, I built a model of angular velocity, right? And then I built a zonation of
answering the question, not telling us what you did.
Can you then repeat? Because I only heard that you asked about the
Yeah, you stressed a lot on the fact that hysteresis affect the effect overall a lot. Could you clarify in what way?
Yeah, because basically this system, as the theory states, there is only one specific angular velocity for the formation of specific amount of modes, right? But I think it shouldn't be like that. There is some zones within angular, the zonation of angular velocities, within which the formation happens, not specific ones.
Okay.
Yes, no?
I just had a question about hysteresis, but I didn't get. So it's not like you think there's some memory in the system, or what's?
Actually, yeah, there is a memory effect in the system.
Okay, can you explain briefly, because it remembers in which state it was, and then depending on that it.
Yeah, because basically there are when you look at the formation of the modes and the transitional process while tracking the angular velocity, basically the angular velocity it doesn't becomes constant once it reaches this specific amount of moles. It's always like it's moving like a sinusoidal, right? Therefore, the system doesn't change constantly. It's taking some
I
time.
put in because they're meant to be short questions, short answers,
Right.
and we're getting a detailed thing. To all three of you, basically, the big discussion was about the experiments and using stepper motors, etc. Do you feel that, opponent, do you feel that it was an appropriate method to gather data?
For the stepper motor?
Well, the stepper motor.
I think
And
it was wonderful. It was used for the initial twist, and then it didn't affect during the motion. So I think it was a really good way to measure them.
Okay, and reporting you.
Well, the initial precession of the stepper motor was important, but while we waited until it didn't have an effect, so that was the only limit.
Okay, thank you. And review?
Yeah, I also consider this to be a good option.
Okay, thank you. Any further questions? Okay, well, we will go straight on to compiling our marks, and thank you. All sit down.
Sorry, is this one?
You ready? Okay. At this stage, we move to our showing of the marks. We'll do reporter, then opponent reviewer. Just to point out, benefit of our juror on the end, and for all of you, that part